I've given you some choices here, and this is one that you don't necessarily have to do the calculation to figure out if the number is correct. The question is, which one of these, just based on the units provided, is the one that's correct?
Is it A?
It's A. Now, a lot of you will fall into the trap and mark D. Okay? Because it's a number we've been beating into people's heads. So that one's an easy one to fall into the trap. Alright? The other one's probably not likely. But D is one that would probably, if I were guessing and I was getting this on a multiple choice test, I would probably see more A's and D's as the answers. And again, it's because you recognize the 9.8, it's a recognizable number, and your eye may or may not notice that it's in meters squared, or it's in meters per second squared versus meters per second. Our eyes do play tricks on this. So that is why dimensional analysis is important, because it's going to help you out to work out a variety of things. So, get ready, because I don't give a study guide. I don't post a study guide for the test. You already have a study guide for the test. But I'm about to tell you what you probably want to include on your cheat sheet for Wednesday. So get ready. Alright, and then I'm going to work a couple of problems just to kind of, because it's been 3-4 weeks now since we did a couple of these types of problems, and so I'm going to do a couple of those, and then we'll cover the last topic in Chapter 3, and knowing full well that the topic that I cover in Chapter 3 today is not on the test, okay? But I do need to cover it because you end up seeing it later on. Alright. What we've covered so far, in Chapter 1, we talked about dimensions, we talked about units, we've talked about conversions. So if I'm making sure my cheat sheet is ready to go, I'm probably going to include on my cheat sheet the conversion between meters and feet. I hope by now everybody remembers that 1 inch is equal to 2.54 centimeters, because that is a fundamental conversion factor that will get you a long way, and it's not one that I typically provide. So I'd have meters to feet, I'd have centimeters to inches, I'd have liters to gallons. Because usually with those three you can get yourself a lot of different places. But we did conversions, and I'm going to do a couple conversion problems after we go through this. The next thing is I would look at vectors, because we have been talking about vectors since the first week. I would look at how do I get a component of a vector. If I give you distance and angle, what are the components in the x and y direction? If I give you the vector in vector notation, can you determine the magnitude and direction from the information? Can you calculate the distance between 2 points? And then adding and subtracting using vector notation. So I would definitely go back and review vectors. Also look at the difference between vectors and scalars. Things like mass, time, don't have direction associated with them. Speed does not have direction associated with it, so speed is not a vector quantity. So speed, mass, time, those kinds of things are not vector quantities. Vector quantities have magnitude and direction. So velocity, acceleration, displacement, when I'm dealing with, I'm wanting to know, did I go forward or backwards? That displacement does have direction associated with it, so it's going to be a vector. So you want to go back and look at the difference between vectors and the mathematical word that we use for those things that aren't vectors and are just numbers. Those are scalars. So we have vectors and scalars. And scalars, think about it, is changing the scale of something. So when I look at Google Maps and I'm on, 1 inch is equal to 500 feet, and then I go to a different map and it's 1 inch is equal to 1 mile, that's a scalar. It's scaling the differences. So we actually use the word to tell us something in terms of scalars. Now for you biology types, there's another meaning for the word vector, but it's very, very similar to the mathematical meaning that we've been using in physics. You talk about a vector for disease, right? If I'm talking about a vector for disease, we know that a mosquito is one of the ways that you can get malaria, yellow fever, typhoid, and a few other lovely things. So the mosquito is a vector, right? So that's another, and you can kind of think of it in the same way because that's a direction or a way. If we think of vector as being a way or a direction, the mosquito is a way that you can contract malaria, typhoid, yellow fever. The mosquito is the deadliest thing known to man. It's killed more people over the course of time than anything else. The mosquito is evil because it is deadly. And if you've ever had the yellow fever shot or the typhoid shot, you know it because it's bad. I used to live in Panama. I lived in Panama for 4 years. So mosquitoes killed lots and lots of people. So vectors, so you can go back to the origin of words to help you out to figure out what some things mean. You'll want to have your 3 kinematic equations, and if you want to put them in for your y directions for gravity, that's up to you. I never needed to because I was saving my cheat sheet space for something more valuable, like example problems. That's one of those things that depending on how you want to do it, it's up to you, but I would make sure I have my 3 kinematic equations on my cheat sheet. You're going to want to be able to find acceleration if you're given distance, time, and velocity, or initial velocity. You'll want to be able to find acceleration if you're just given velocity and time. You're going to want to be able to find acceleration from a graph. So you want to look at how to get acceleration. You want to look at how to get velocity. If you're given distance, acceleration, and initial velocity. Or you're given just distance and time. So you want to be able to calculate acceleration and calculate velocity. And you want to be able to calculate distance, depending on what information you're given. Could be just acceleration and time, could be velocity, could be you want to be able to manipulate those 3 kinematic equations. You'll want to review. You'll want to definitely look at your building problem where you toss the ball up and it falls back down. So if there's any example in the book that you want to go back to, it's that one. And you want to go back to its partner where the ball goes off like that. Okay? This is the 1-dimensional, and this is the 2-dimensional. 1-dimensional and the 2-dimensional. So you want to make sure that you've got those 2, because the other one that you want, other example that you want to look at is the airplane that's dropping the package. So these 3 examples, if I didn't go back and look at anything else, I'm going to go back and look at those 3 examples. And finally, you want to review the graphs. So I want to look at my position versus time and my change in velocity versus time. and what those graphs are telling you. So go back and look at those chapter 2 problems where you were calculating average velocity from the graph. You were looking at those graphs to understand what they meant. So you definitely want to be able to look at your vectors and look at those pieces. You'll probably also want to review either the mountain problem or a couple of other problems where you're looking at, I'm from here and I want to figure out either this distance or I want to figure out that distance, looking at that basic type problem. The height of the waterfall, the height of the fountain, there have been a couple of different problems along that line. And that reminds me about the pre-work. Okay, chapter 4 pre-work apparently has a lot of Flash Player on it. I know some of you are not able to access Flash Player. And I'm actually using this semester to try and remove my Flash Player from my assignments. Unfortunately, my computer, my desktop computer, is not clearly identifying to me which ones are Flash Player items. I have to actually go to another computer, like the computer I have over here in Enid, to try and figure out which problems I need to be pulling. And I think almost all of the chapter 4 pre-work, because I was using active examples to kind of help you start looking at how to manipulate vectors even more than what we've been doing so far. I think they were all Flash Player. So I am not worrying about, I'm going to go in and look at this homework. I haven't had a chance. When I went in to try and fix it yesterday, I discovered that my computer at Tonkawa, my desktop computer there, doesn't clearly identify them. So it was like, okay, I don't know which ones I need to pull, which ones I need to switch, and kind of looking at them, it's all of them. So right now, the pre-work for chapter 4 is not going to count for anybody. I mean, it's going to be there. If you want to go back into it, great. If you can actually access it, great. But I am not going to penalize anybody for the pre-work of chapter 4. And I'm going to try this weekend to start looking at some of the other ones that are upcoming to try and figure out where all my Flash Player problems are, so that I can get them switched over. Which is kind of a bummer because this pre-work, these simulations, are really, really good to help you kind of understand a few things. And that's just, so I understand the frustration on that one. So chapter 4 pre-work, it's not going to go into the grade book at all. So don't stress about it, don't worry about it, because that's an issue. My understanding is Flash Player is going totally away within the next year. And so it's just, it hasn't been converted to HTML yet, or HTML5, and I've got to start taking those problems out. And I just didn't get to it for chapter 4, or the pre-work for chapter 4. So don't stress about that pre-work, because I know, and on top of that, I know the weather ended up contributing to a few things for some people, but don't sweat it, because I already had decided chapter 4 wasn't going to be a problem anyway because of the Flash Player issue. Okay? Questions so far? All right, I'm going to put up this sheet. I don't know how well it's going to go, but I will try to also get my okay, we're not going to be able to get all of that. Well, down here at the bottom, it's just review the graphs piece, that part, and this up here at the top. That way you can take a picture with your phone, or you can, I should be able to get this uploaded today, but it's in the recording that this is, if I were making my cheat sheet, because I don't post a study guide. Your study guide is your homework, and we've already kind of talked through the best way to study for a physics test is to go through and look at the summaries of each of the chapters and look at those examples and know which examples that I've harped on, because you're likely to see those kinds of problems on the test. We good? Oh, you're all trying to, is it not going over? Or is it fuzzy on the big screen in there?
Fuzzy on the big screen.
Okay.
Yeah, we just get a little clearer picture on this one.
Not a problem. Not a problem.
Yeah.
And for those of you who, depending on what you want to look at, I know there's a really cool app. It's called Office Lens. And what it will do is if you're taking a picture of a screen, you're taking a picture of a piece of paper, you're taking a picture of a whiteboard, it actually will focus in on that screen and whiteboard and cut out the extraneous information. And it is a free download. I have an Android system, and I've used it on my Android. I don't know if the Apple system has something similar. The one I used to use was called Camera Scanner, that was using it as a scanner on your phone, but Norton and a few of the other ones are saying apparently that one's been hacked. So I have removed my Cam Scanner off of my system, but I will tell you that Office Lens is the current one that a lot of professionals are using when they're going to conferences, they're going to places to capture screens. All right. So good, everybody got the information that they want? All right. So let's do a couple estimation type problems that we did way back in the first week. Okay, way back in the first week. And I've actually picked one that's for you medical types. That's going to make a little bit more medical sense. Actually, the human heart can pump up to 7 liters of blood per minute. Average is about 5. And that's also highly dependent upon the person itself. But the average is about 5 liters per minute. I've been practicing. Anybody got an answer yet?
7,200.
All right, I got somebody that says 7,200. Anybody get any other answer? That's what I got too. So let's do it. You take 5 liters per minute. And there are 60 minutes in 1 hour. And there are 24 hours per day. and that's gonna give you 7,200 liters. And I don't know about you, but 7,200 liters isn't a number that I can kind of imagine. I sort of can because we know what a 2-liter bottle of pop is, right? So if I did that in terms of bottles of pop, that's 3,600 bottles of 2-liter bottles of pop that your heart's pumping through a day. If I'm not even familiar with that kind of a volume, 1 liter is equal to 0.26 gallons. Okay? And so I'm going to take my 7,200 times my 0.26, because this is in liters, this is in gallons per liter. That's going to give me 1,872 gallons and that's a pretty big number. So your heart is a really, really good pump. It's an extremely good pump. Okay, we'll do another one, because when I guess it was Hugo was the one that hit Houston and dumped all that rain on Hugo. I did a column on just how much rain that was. Well, yesterday, the interesting thing about it, depending on where you were yesterday, you either got a normal rainfall. In fact, the Ponca City Airport said over the course of 3 hours that it only got an inch of rain. But if you have friends in Ponca, you saw the flooding on South Street right near the refinery. And I'm going, okay, the airport said we had about an inch. So I called up the weather, and there was this little tiny pocket that it said that was something between 3 to 5 inches of rain. Well, those of you who live on farms around here or have acreage and pastures know that there's something called farm logs that can give you the rain for your particular pasture that you're working with or your particular acreage that you're farming. Well, I have a plot of approximately 12 acres, although when you GPSed it out, according to farm logs, it's 11.4 acres. And it was closer to the area where everybody was getting all the flooding. So I have 11.4 acres. And it got 4.1 inches of rain in that same 3-hour period that the Ponca City Airport said it got an inch. So, I want to know the volume of water that was placed on my property in that 3-hour period that we got 4 inches of rain. I don't know if you guys know how inches of rain is done. Basically what they have is it's an area that they're looking at, and it's usually a standard area. That's why you get a rain gauge. And it is how much water it takes to create 1 inch of rain in that standard unit of area. So 4.1 inches would be the height that I'm dealing with across the square footage of my acres. So that's how rain is actually measured. So if I start out with acres, I have 11.4 acres. This is one of those weird conversion factors that you may have to look up. 1 acre is 43,560 square feet. And 1 foot is equal to 0.3048 meters. And we know that 1 inch is equal to 2.54 centimeters. And 1 cubic meter is equal to 264 gallons. And to put this in perspective, a standard bathtub is 80 gallons. Because we all have a pretty good estimate, we know what a bathtub looks like. A standard bathtub is 80 gallons. So let's do it, because I haven't done it yet, so we're gonna do it. So I'm starting out with 11.4 acres. And it's 43,560 feet squared divided by 1 acre. Now I could do this in one fell swoop, but I'm not going to. I'm going to do it piecemeal. Just because we're going to get some big numbers along the way. So this is 496,584. And I am not going to worry about significant figures until the end. All right, I'm going to keep my interim figures. And this is now in feet squared. Okay? So this is area. I want to go to volume. I'm in feet. So 4.1 inches is, I can do 12 inches. Well, let's do, yeah, we'll go ahead and do it that way. So 4.1 inches, and there's 12 inches per foot. So this is going to give me in feet. That's going to be 0.342 feet. So the volume in cubic feet, because it's going to be the area times the height, it's going to be that times 496,584. 16966.2. And that's cubic feet. And that's how many cubic feet of water was dumped in a 3-hour time span. So now I'm going to go from there to cubic meters. So to get to cubic meters, I have to do 16666.2 feet cubed. And I have 1 meter is equal to, or let's do it this way, 0.3048 meters is equal to 1 foot. But I have to cube that in order to make sure I've got it together. So I'm going to do times 0.3048 times 0.3048 times 0.3048. This now gives me 4804 meters cubed. So now I'm going to take my 4804 meters cubed, and I'm going to put that into gallons. And 1 gallon, or it's not 1 gallon, it's 264 gallons is 1 meter cubed. Gives me 126,836.4.7, or 1,268,364.7 gallons. Now if I divide that by 80, that's going to give me bathtubs. 15,854 bathtubs. If you start putting that into perspective, Tonkawa has a population of about 3,600 people. There's 5 bathtubs full of water for every person in Tonkawa. That was dumped on only 12 acres. Now you understand why we get flash floods. Water, that we just can't handle that amount of water in that short period of time. There's just no way. 1 inch of water is a lot of water. It's a lot of water. Now you think about what happened with Hugo. 36 inches of rain fell over the city of Houston in a 48-hour period. That's like dumping, I calculated how many Kaw lakes that was. And it wasn't an insignificant number. So we had a lot of water. Had a lot of water yesterday. Okay, so we're good with conversions, good with estimations, good with rates. All right. So there's one less part, or one more part of chapter 3 that we have to talk about. And I don't even recall if there was even I think there was a couple homework problems on it, but it's the homework that's due like right before class or right after class on Wednesday. And that's relative motion. And I don't test over relative motion, okay? I don't test over relative motion. I do have to introduce it because we will use it down the road. And it's something that will help explain a variety of different things. But for what we're doing right now, I just am introducing the topic because we've got to move on to other stuff. So if I'm on a train, okay, so I've got my little train car here. Okay, and we know if I'm in a train car following my train, and I've got a person that's standing over here at the intersection, and if the train is moving at a velocity of 30 meters per second as it's passing this person, and all of a sudden I see a person in the train moving 2 meters per second towards the front of the train car, this person is going to see this person moving at 32 meters per second. Because this person is moving with the train car, so I'm going to draw the picture of the train car. This person in here is moving at 2 meters per second, but the train car is also moving at 30 meters per second. Even though this person says I'm only moving 2 meters per second, relative to the objects that are in the car, the person that's standing out here, that's observing the whole thing, is seeing this person move at 32 meters per second. And it's because I'm getting a vector addition. Okay, I'm adding the two velocity vectors together as this person sees it. And we can do a similar thing if I'm on the rail car and I'm moving this direction towards the back, and I'm moving at 3 meters per second towards the back. I have the vector that's 30 meters per second, but I'm going back 3 meters per second, and that's 27 meters per second as this person sees it. Hence the term relative motion. This isn't the relative motion that Einstein's talking about. This is legitimate relative motion that we all experience every day. That's why, if you're walking on the moving sidewalk, that you get to the other side faster. Because if I'm walking on the moving sidewalk, okay, I'm walking on the moving sidewalks usually going at about, we're gonna call it about 2 meters per second. And if we can walk on the moving sidewalk at 2 meters per second, we're crossing that distance that we have there at 4 meters per second. And we all have had the little kids, or we've all done it ourselves, that in order to stay in the same place, I can be walking this way at 2 meters per second and I'm not going anywhere. I'm staying to the person who's standing out here in the breezeway, I'm looking like I'm not going anywhere. Because I'm walking at the same speed that the moving sidewalk is going, and those two vectors are canceling each other out. So in terms of relative motion, I'm canceling it out. I'm not changing my position. But if I'm talking about what I'm actually doing, I'm actually moving at 2 meters per second. But my sidewalk's moving the other direction, so I'm not moving anywhere on my moving sidewalk. Similarly, you can do it on boats, on airplanes. It's that relative motion dependent upon where the observer is. Because if I'm the observer on the moving sidewalk, I'm going a certain I'm going at a certain pace. And that covers what's left of chapter 3. Do I have any questions? So you should have everything that you need for the homework. I would suggest that second part, chapter 3, part 2, I would suggest going ahead and getting it done before the exam because there's some more projectile motion problems in that one. I would not worry about studying for the relative motion for the test because there are no relative motion items on the test. And I will not test over relative motion. So it's there. We've got a couple homework items on it and we've covered it. But we're going to start on a week from today on forces. I will be in the physics lab over here at 1:30. And for Tonkawa, I will be in the physics lab at 12:30 on Tuesday. For anybody who wants to come. Yeah.
What are the specifications